Record on this computer. Okay, so before we start the lecture, are there any questions about course logistics or from last on Monday's lecture? Nothing? Okay, anything online? No? Okay, so today we're going to continue with encoding with gradients. We'll get up to the MRI signal equation, and we'll talk about case-based trajectories and pulse sequences. So today is the first day you'll sort of hopefully understand what happens on an MRI system in terms of the acquisitions that's happening. And if we have time, we'll get to sampling, aliasing, and discuss sort of what the sampling requirements are for MRI. Okay. Okay, just to remind you, we talked about polarization. That's the B0 field, right? We talked about excitation, which is the B1 field. And right now we're talking about the gradient coils, which do encoding. So remember, what we're encoding is the gradients are changing either the frequency or the phase. The frequency and phase are related. Okay, the gradients are not, at least in this discussion, not affecting the polarization. Okay, so really gradients are frequency and phase. Okay, so I think that came up on one of the pre-lecture quizzes. And then the RF coil, as we'll see later today, has a second role, which is it's going to integrate the signal over our entire sample. Okay, so the two things we're going to talk about today are these two, encoding and integration. Just to summarize what we talked about last time, basically, when we excite the spins or the magnetization, it precesses, right? And so let's say we excited it with a 90-degree pulse. It's going to start off here, and then it's going to precess in the transverse plane. There's going to be T2 decay in the transverse plane that affects the MXY, and then there's T1 recovery, okay, or T1 relaxation. Okay, and that's for the M sub Z component. So basically, while this spin is in the transverse plane, that's when we have time to measure the signal. And remember, we said that the T2s, let's say, for many tissues on the order of, say, 10 to 100 milliseconds. Okay, there can be things that are shorter or longer, but a good rule of thumb is we need to be able to acquire the data on the order of 10 to 100 milliseconds, and sometimes even faster, all right? Because basically, we wait longer than that, then this transverse component has decayed away, and there's no signal for us to detect, all right? Okay, so just to remind you, we're talking about the gradient fields, and the gradient fields just cause spins at different locations. To here at the isocenter, we assume that the phase is going to be 0, okay? So at the isocenter, and then as we go off here, the spins will, if there's a positive gradient, then these spins will spin faster, and they'll get more and more negative phase. And then these spins will spin slower, so they'll get more and more positive phase, okay? Now, it's important to remember that we could also apply the gradient this way, okay? So we don't just have to apply a positive gradient, and we'll see later we apply negative gradients, in which case now these spins will spin slower, okay? And these spins will spin faster, all right? So that's one of the degrees of freedom we have with the MRI. Okay, so just to remind you, our interpretation is essentially we use these gradients to have different sort of patterns of phase in our sample. And we're going to spend a lot of time today talking about those phase patterns, and in the upcoming homework, there'll be a problem just all about phase patterns, okay? So we want to make sure you understand that today. Just to remind you, here in this row, the phase is, there's no variation in phase across the sample, okay? So we call that kx equals 0, right? There's 0 frequency there, okay? If we go to the next row, we can sort of see there is a variation in phase, and half a period of that is 4 delta x. So one period would be 8 delta x. So this corresponds to a spatial frequency of 1 over 8 delta x, all right? And so if you see a spatial pattern like this, you would say that corresponds to kx equals 1 over 8 delta x, all right? And then if we go to the third row, you can sort of see now it takes 4 delta x to go one cycle. And so we say the period is 4 delta x. And so there we would say that the spatial frequency is 2 over 8 delta x, which is also equal to 1 over 4 delta x. All right, so that's the basic idea, is basically these gradients impose different spatial patterns, and those are exactly the spatial patterns we need for a Fourier transform. So basically, each of these terms is of the form e to the minus j 2 pi kxx, right? So basically, that's what we need in our Fourier transform. So the gradients actually, the remarkable thing is the gradients actually impose that phase pattern onto the spins themselves. Okay, so to recap, if we have a constant gradient on, then the spins will process at different frequencies. And so at each point in time, there's going to be a different spatial frequency of the phases. And if we leave that gradient on, then the spins get more and more out of phase. And so we go to higher and higher spatial frequencies. Okay. And so the gradient allows us to implement this complex exponential. Okay. So the nice thing about MRI is this complex exponential is not just a fictitious complex exponential. It's really actually imposing on the phase of the spins. All right. Okay, so let's review the 2D Fourier transform. So now we want complex exponentials that depend on both kxx and kyy, because in general, we're interested in two-dimensional images for this class. Obviously, we can go to 3 dimensions, and actually in MR, you can actually go to even higher than 3 dimensions, because you can start not just encoding position, you can start encoding velocity, acceleration. So you could go to 6 dimensions, you go to 4 dimensions like space and time, you go to 9 dimensions, space, velocity, acceleration, and then if you add time, that's 10 dimensions. So there's lots of dimensions you can go to, okay? So today, for this class, we're just going to talk about 2 dimensions, but just know that MR is very rich in the sense that you can actually have n-dimensional data, okay? So the basic idea is this is what the MR signal is going to look like. Okay, and that's what we're going to work up today. And so then we take that MR signal, we gather the data in K-space, and then we put it into MATLAB or Python, and then we do an inverse Fourier transform, and we get back our image. Okay, to first order. As we'll see, this can be more complicated than that, but this is the basic concept we want to go over today. Okay, so just to remind you, so we talked about image space and K-space. Remember, the center of K-space for most objects is this highest point because it's basically the sum of all the protons in your object. Okay. We went over this example last time, and we said that places along in here in K-space correspond to edges, right? And so if I get rid of those points, if I just zero those points out, then these edges here, this vertical edge here becomes quite blurred out, okay? Whereas this horizontal edge stays relatively sharp, okay? There's other examples in the supplementary video that you can take a look at. Another interesting thing that you see sometimes in MRI, although you don't want to see these, are sometimes you'll see these what are called corduroy patterns or zebra patterns in your image. These occur when something has gone wrong, okay? And so basically, imagine, so this is the Fourier transform of my object, and let's say at some point in time, someone just injected some energy here, okay? This could come from, for example, maybe someone opened the door at that point and some RF energy got into the room, or it could even happen when someone didn't screw something down and there's something's vibrating and just metal hitting each other can induce enough energy that the MR signal picks it up, okay? So we occasionally see this, but we try to make sure we don't see it. But this is an important example because remember, if this is Kx and this is Ky, right? I go from the center of K space and I can always draw a vector out to that point. And then the picture we have is then the interference is perpendicular to that vector, okay? If you're familiar with electromagnetic waves, right? You have the K vector, right? And the wave fronts are perpendicular to the K vector, right? From physics, right? So it's the same thing here. So if you see a point in K space, just draw the K vector out to that, and then you know the pattern it corresponds to is perpendicular, all right? So for example, here, if it happened here, then the K vector goes this way, and you get these stripes, okay? So, so yeah, I mean, that's sort of interesting. So if you ever get an image like this, you know, in a clinical exam, you'll have some idea of what happened, right? You'll know, okay, well, there must have been something in K space that happened at that point, okay? generally they see this, they'll redo the scan. All right. Okay. So this is just reminding us of, so far we've talked about, okay, we're at some point in K-space and it corresponds to some pattern like this, right? But this is sort of simplifying the view. What we really want to do is go from this sort of simplified view of just stripes to actually this view here, which is, this is really what the complex exponential is, all right? And these are what we're going to get the spins to do. And so you can sort of see here that you can sort of see the pattern here. There is, all these spins are sort of have the same phase. Along the lines, the diagonal lines, the spins have the same phase, okay? So now in the spin domain, basically these stripes correspond to, if you look down any one stripe, those spins will all have the same phase, all right? And so that's basically, you're imposing spatial patterns of variation. So that now the spatial, if you go along any diagonal here, you're showing the spins are varying along this line here, okay? Just showing, this picture is more just showing that the reason why Fourier transforms are so incredibly useful is that these stripy patterns happen a lot in both nature and especially in the man-made world, right? I mean, obviously, this is probably somewhere, I don't know, in London or the Netherlands, just a lot of row houses, right? So obviously, this image would be fairly well represented by these stripes, okay? So it just turns out that even in your brain, you have essentially like Fourier detection in your early visual system, okay? Just because it's very useful to be able to see stripes and patterns in the real world, right? Okay, so let's sort of keep building up our intuition about what it means to be at different points in K-space and what the spin patterns look like. So at Kx equals 0, Ky equals 0, that just means there's no variation in phase, either in the X and Y direction. So this is typically the starting point for most MR experiments. We start off, we tip all the spins, and at time equals 0, they're all in phase, all right? So that's where we start off. Now, let's say we apply a gradient. In this case, we apply a gradient in the Y direction, right? Okay. So at some point in time later, I'm still at Kx equals 0, right? Because if I go along the X direction, there's no variation in phase. Along any row, there's no variation in phase, right? But if I go along Y direction, there's clearly a variation in phase, okay? So this corresponds to Kx equals 0 because that's 0 frequency in the X direction, but there's clearly some frequency component in the Y direction. So that's at some value, Ky is not equal to 0, okay? Okay, so let's take a look at some examples. I think you'll see similar patterns in the upcoming homework. So this is Kx equals 0, Ky equals 0. And so you sort of see all the spins are aligned the same way, okay? This is Kx equals 0.25, Ky equals 0.5. So let's see if that makes sense. Well, Kx equals 2.5 means the period would be 4, right? So the period would equal 1 over that. So in fact, if I go from here to here, that period is 1, 2, 3, 4 steps, okay? And then this is saying that the period would be 2. And if you look at that, yeah, the period is 2. It takes 2 steps to go all the way back to the same phase, all right? So if you're trying to figure out the frequency, you can always sort of see how long does it take, what's the period for repetition of the phase pattern, and then 1 over that gives you the spatial frequency, all right? Let's look at this one. Kx equals minus 0.25, Ky equals 0.5. So this also has a period of 4, right? But what's different, and Ky is still 0.5, it has a period of 2. What's different about this? We've got a negative sign here, okay? So what does that mean? Remember, we have the term is e to the minus j 2 pi kxx, right? So if kx is greater than 0, then we know that theta is going to be less than 0 as x for x greater than 0, right? Because we've got this minus sign there. So let's see if that's the case. As I go along in the x direction, yeah, theta is going to minus 90 degrees, minus 180 degrees. So this, from the center to here, there is a negative angle. So we know that's kx equals 0.25. Whereas here, kx equals minus 0.25. So notice as I go from here to here, it's positive 90, okay? And then here we have kx equals 0.25, ky equals 0. So this is still the positive spatial frequency. And then here, we're just seeing no variation along the y direction. So that's ky equals 0. All right. Okay, so I don't remember why I have this slide here. Okay, we're going to skip this. Okay. Oh, no, I remember why we have this. Okay. So far we've talked about this part. Okay, we have my object and I impose a spatial pattern on it. Right. Now, mathematically, this is a multiplication, right? Okay. But in MR, it's not like we have some multiplying sort of thing. It's not like there's a calculator we put into the object. The way we do the multiplication is we just impose this, we just make the spins at different locations be in different orientations. So that's essentially that multiplication. Okay. So the next step we want to talk about is how do we do this integration? Okay, so that's integration, right? Okay, so let's work up to how we do that. So basically we can, so the gradients do the multiplication for us by getting the spin patterns. And then the next question is, let's look at that in a little more detail. And then we're looking at the integration next. Okay. Okay, so we've already looked at this sort of simple picture here, but I'm at some point in k-space, it corresponds to some spatial pattern like this, right? And the gradients sort of do that implicit multiplication for me, right? And then what I want to do is I imagine taking this object and imposing some spatial pattern on it and then summing up all the spins over some volume, okay? And that will give me the Fourier transform at this point in k-space, okay? And then I go to another point in k-space and I do the same thing. I get the spins to have some other spatial pattern and then I sum up over all the spins and that would give me the Fourier transform at that point in k-space. So MR is like, instead of going projection by projection by projection, you're sort of going point by point in k-space, okay? Now you can make MR look like CT, which we might talk about in the future, but for now, just the most basic concept is you're essentially sampling k-space, okay? Okay, so this was a sort of a simple picture with stripy patterns, but really the more physical pictures were imposing these spatial pattern of the phases, right? This is actually what the gradients are doing. And so this multiplication is not, it's just implicit by imposing the gradient pattern, spin pattern onto my object. This multiplication gets done for me, and then I integrate over this volume. And here, now the phase pattern is in the ky, so there's y variation, there's no x variation. I impose the spatial pattern onto my spins, and I integrate, and that gives me this place in k-space, right? Okay. So let's talk a little bit about what happens when I integrate all the spins and how that's related, how that spatial pattern is related to the value of the Fourier transform. Okay. So let's imagine this is my object here. Okay. Okay. So let's just assume it's like, I don't know, like it's something, let's say it's a piece of chocolate that has enough water in it that there's enough proton spins that we can detect, okay? So I impose a spatial pattern like this, right, which is a diagonal pattern, right? So I'm at some point in kx, ky, right? So if I think about summing up all, now the formula says now integrate over all these spins, right? So then if I think about this, if I have a spin like this, it sort of cancels out the contribution from a spin here, right? Or this spin, for every spin, I can sort of find a spin that sort of cancels out its contribution. Okay, so if I think about the resultant vector, it's going to be pretty small. Okay, because this is a square. Whoops. All right. This is a square object, and it doesn't really match the stripy pattern very well, right? So that just means that if I look in Fourier space, at that point in k-space, the Fourier coefficient for this bar at a stripy pattern location should be relatively small. But now let's say I take the bar and I just cut out sections of the bar, right? So now the object itself is stripy, right? It's just diagonal stripes of chocolate with protons in them. And now you can sort of see for this spin, there's really not a spin that's going to cancel it out very much, right? And so now when I sum up all these spins, I get a pretty big number. Okay. And so that's the idea that when the Fourier transform pattern, the spatial pattern matches your object, then you expect that Fourier coefficient to be relatively big. Okay. So the integration is what does that for you, right? You're integrating over all these different phases. And if the phases line up, you get a big number. And if the phases cancel out, you get a small number. All right. This concept of phases summing up and and giving things actually turns out to be everywhere in physics. For example, does anyone here know heard about the Feynman path integral? Okay, so basically in quantum mechanics, there's this idea that if you go from here to here, in reality, you take every possible path from here to here. Okay, it just turns out that, and in the quantum world, you can actually take a lot of these paths. But in our world, because of the, we're so big, that this is the most probable path to take. And that's the path where all the phases line up, okay? And so the probability along the straight path or the path of least action turns out to be the path where it's sort of like where all those phases line up, okay? So this concept of phases lining up happens everywhere in engineering and physics, right? Okay, so let's talk a little bit about how we integrate the signal. So the nice thing is the integration sort of comes for free, right? Basically, if I have my object here, let's say this is my object, and I have an RF coil, okay, and let's say the RF coil surrounds my object, and then it basically is sensitive to all the spins in my object. And so it basically does the integration for me. Okay, so it's really the RF coil sensitivity. And so, for example, if I have a human being and I put them in a coil like this, and this coil picks up the signal from all the spins there, then that essentially is how the integration is being done. Okay. Now, it used to be most MR, let's say 20 years ago. Yeah, 20 to 25 years ago, most systems just had one coil. Okay. And that's all you had. Right. And maybe you had one coil that was for the whole body and maybe another coil for the head, but it was just sort of one channel. As we'll see in a couple of lectures, right now, if you go get an MRI done on you, you're going to have lots of little small coils. So each little coil, which is called a surface coil, will only integrate over a small section now, okay? And that turns out to give you some flexibility in the reconstruction, allows you to go faster, okay? But for now, just imagine we're integrating over the whole object. Okay, so here's the recipe for the 2D Fourier transform, right? So the 2D Fourier transform says, take your object, multiply it by this spatially varying phasor pattern, and then integrate. Okay, so creating the spatially varying pattern is done by the gradients. Multiplying the object is essentially just implicit because the gradients are acting on my object. Okay, so steps 1 and 2 are what we call encoding. And then step 3 is just integration. Okay. And the cool thing about MR, I'm not sure we'll get to it this year, but it turns out the integration doesn't have to be performed in the same place where you do the encoding. So you can actually manipulate the spins here and then ship the signal to somewhere else and measure it somewhere else. So that's also a pretty cool thing. So you could actually, there are experiments where you actually create the phasor pattern here and then wait for it to move someplace else where maybe you can measure it better, or you want to see where it's delivered and then you measure it somewhere else. So MR has a lot of flexibility, and you can sort of divide those two parts in two. Okay. Okay, so let's see where we're going. Okay, so let's just go through this and just sort of work up the intuition. Okay, yeah, we're gonna work up to some. Let's see. Okay, yeah, we're gonna work up to that problem. So so let's just do some examples to help you build up your intuition of what's going on. So this I know is going to be hard to see. So I posted a visual, a movie of this on Canvas, so you can look at it, zoom it on, but I'll walk you through it so at least you understand what's going on. So this is my simple object I create. So these are zeros, ones, zeros, one. So this is obviously a stripy pattern, right? I've created like an artificial stripy pattern for you, okay? This is the orientation of the spins, and you'll see there's a spin everywhere. So this is essentially, this is the spatial pattern that the gradients want to create, okay? And then this times this is this. So this is the spin pattern imposed on my object. So where there's no spins, it's just 0. Okay. And the multiplication is just done because there's no spin there. So there's nothing there. Okay. And then this is the summation of all these spins. So that's the vector sum of all these things. So you can sort of see that. So this is, you can't really see it here, but all these spins are aligned. So we're starting off at kx equals 0, ky equals 0. And you can sort of see at that pattern, there's still a pretty good summation of spins because all these line up, right? And that's just saying that's the center of K space, right? That's just saying, hey, there are protons there, right? So those still sum up, okay? But now I'm going to go through this movie, and what I want you to watch first is just watch this pattern, okay? We're going to play the movie and just watch that pattern. So you can sort of see it's sort of starting off having some vertical lines and then getting to diagonal lines, okay? So now I'm going to go through it slower so that what you can do is we're going to sort of look at this, and we're going to look at when this gets big again, okay? So let's just go through a little more slowly. You can sort of see it's getting smaller. So here it's actually that summation's gone to 0, right? And so I've got some weird spatial pattern here that's really not a good match for this object, okay? So let's just keep going until that thing gets bigger. Here it's getting, where does it get big again? Okay, we must have missed it. Here's where it seems almost as big, right? And so you can sort of see here that this spatial pattern is looking like it might be a good match for this object, right? So then that summation gets big again. And then it gets small, and then it stays pretty small because none of these other stripy phasor patterns is a good match for my object, okay? Oh, wait, there it is. No, that's the beginning. Okay, so the beginning is big, and then somewhere where I've got something almost vertical is big, okay? So you can play with this on your own and see that, all right? Okay, so let's just sort of take that, do a few examples of this. And so let's say this is my object, it's all ones, okay? And I multiply by this spatial pattern. So the vector sum here is just sum of all these is just 25, right? If each of those has a value of 1, it's 25. And then here, if my object now is, let's see, these are 1s and -1s here, right? Then essentially what I can think about doing is, let me change the color here. Whoops. Okay, so everywhere there's a 1, I'm going to have some contribution like this, right? Because the 1 times that is like that. But every time I have a -1, so all these are -1s, it actually flips the spin that way. Okay, so then the vector sum here is 6 minus 7 is -1. Yes.
Is this element-wise multiplication, or like,
Is it all what?
Element-wise? Like,
oh, element-wise. Yeah, element-wise multiplication. Yeah. So if you go back, that's a great question. So if you think about this, right? Gxy times e to the minus j 2 pi kxx plus kyy. That's basically element-wise multiplication, right? Every x location is multiplied by its phase at that x location. Yeah. Question.
It seems like kx and ky control the resolution pretty much.
Yes.
So unlike CT, where resolution is dependent on the detector element, here it's actually dependent on how well we can control kx and ky.
Yeah, that's right. Yeah, so I'm not sure, we'll either get to it today or on Monday in terms of the actual Nyquist requirements for MRI. So it turns out that it's in terms of, as compared to CT, MRI is much more flexible in terms of you basically can trade off time versus resolution. Yeah. Okay. Because basically it's just a matter of how far you're willing to go into K space, right? So if you have so for example, certain experiments where they want really high resolution, like let's say you get a dead brain, you take the brain out of the head, you put it in formaldehyde, and then you can just scan it for like days and get super high resolution because you can afford to go out to really high parts in K space. For a human being in the ER, you maybe only have 5 minutes, right? So you're on the clock, right? So that's the trade-off, right? It depends on what your sample, or the other thing where you really have to go quickly is little kids or babies, right? Basically, you either have to figure out a way to scan them very quickly or figure out how to scan them even as they're moving. Okay, so that's the trade-off. Okay, but yeah, those are great questions. Okay, so everyone okay with this example, the vector sum? Okay, yes, question.
You said if you scan longer to get better resolution.
Yes.
Is there ever a plateau where increased time will increase resolution?
In principle, yeah, I mean, once you hit like the atomic level, right? But where you're really going to be dominated by is there's diminishing returns, right? Because at some point, your object may not have any energy out there. So it's really, so that's where it becomes, what resolution does your object actually have, right? And then how much energy is out there. But yeah, in principle, the longer you scan, the more you get. Now, the other issue though is contrast, which we'll get to later, is basically even if you have very high resolution, but there's no contrast at that level, then you're not getting any more information, right? So for example, in the brain, maybe the contrast you're looking for is like in the brain, there's different layers, right? But within every layer, you may not have enough contrast to differentiate within the layer. So if you scan beyond that, then maybe you're not getting the information you need. But yeah, in principle, you could just scan forever. But in practice, the other thing is also the system itself is not like, if you scan for 24 hours, the system is drifting, things are happening, the B0 field is drifting, things are happening that it's not like perfect. Okay, so you'd have to correct for all those things too. Okay. But yeah, that's a good question. Okay, let's take a look at a few more objects. So let's look at this one here. Okay, so this is a different spatial pattern. So let's look through this. So is there variation in the x direction? Yeah, there is, right? So first question is, what's the period here in the x direction? Let's call it. Anyone? 4, yeah. So we're at kx equals 1/4. So the question is, are we at plus 1/4 or minus 1/4? So if I look at, I'm here at 0 and I'm going along here, we're at minus, right? Because we're having a positive theta as we move along x, right? So we're at minus 1/4. And what about ky? Where are we in ky? The period here is also 4, right? Right. So at 1/4. Now are we at plus or minus 1/4 here? So now by moving the positive y direction, which direction is the phase going? Is it going clockwise or counterclockwise as I go from here to here? Yeah, clockwise. So then we're at plus 1/4. Okay. Let's take a look at this spatial pattern down here. So now the period is 2, right? So we're at kx equals 1/2. And now the question is it plus 1/2 or minus 1/2? We can't tell, right? Because at this resolution, there's no information. So that's going to be something we'll talk about when we talk about resolution aliasing. Similarly here, the period is 1/2, but once again, we don't know whether it's plus or minus 1/2. Okay. Okay. So now if we look at this object, we can think about the vector sum. So I think I can just draw this like this, right? Just take those spins, and the other spins, I just negate them. So now when my object is multiplied by my phasor pattern, I get something minus 13. Okay. And similarly, if I do this guy here, it's all like this, right?
Can you explain why all the red and blue are left there, even though they're ones and negative ones?
Yeah, so this is 1 multiplying this guy, so that leaves it alone. This is minus 1 multiplying this one, so it flips it that way. Yeah. So there's a good question. What is an object with -1, right? That's sort of weird. So so it actually turns out that, obviously, this is not going to have any negative protons in it. But later on, it turns out that if we actually if spins are flowing, we can actually sensitize the MR to the direction of the flow. So this might be a voxel that has blood flowing one way, and this would be a voxel that has blood flowing the other way. And that actually can flip the phase of the spins. Okay, so it turns out that phase, for most of this course, we're going to talk about phase in terms of a static object. Towards the end of the class, we'll talk about, well, what happens when spins are moving? It turns out you can actually make the phase sensitive to the velocity, right? Okay, so we're going to look at this example here, and this is an object which is just all ones everywhere, and this is the phasor pattern, and we're going to look at this summation as that phasor pattern changes. So I think oh wait, is it working? Maybe it's not even working. Oh, it's just going too fast. Okay, all right. So basically, the main thing is, as I go to different spatial patterns, the summation is very small because, oops. Yeah, sorry, I need to slow down this movie. Okay, maybe for next year we'll do that. Anyways, the idea is that the spatial pattern only really matches when it's at kx equals 0. Here, this might be a better example. Now I've got a stripy object, right? So I would expect it to be bigger. Yeah, sorry about this. We'll have to fix that next year. Okay. Anyways, let's do this. Let's do this exercise together. So here is an object with ones and zeros. Okay. And let's just walk through this example together. So the question is, for every one of these A, B, C, D, or E, what is kx and what is ky, and what is the vector sum that I'm going to get? Okay, so since it's relatively small class today, let's just walk through this in person. So A, where are we in case space for A? What's kx equal to? 0, right? And similarly, ky equals 0. And what would be the vector sum of the spins? So what? 5, yeah, sorry, yeah. Okay, great. So how about B? Where are we in kx here? 1/2, yeah. Plus or minus 1/2, we don't know. And ky equals? Right. And what's the vector sum here? Yeah, -3, right? Okay, -4 plus 1, -3. Okay. What about C? Where are we in kx here? Right? And ky? 1/2. And what's the vector sum here? Also -3, right? Right, because I basically, where it's 0, I don't have to worry about those spins, right? Okay. All right, so let's keep going. Kx, ky equals. So where are we in kx here? 1/2, right? And where are we in ky? 1/2, right? And what's the vector sum here? 5, yeah. So basically, we find out at kx equals 0, ky equals 0, the vector sum is 5. And it's also 5 at kx equals 1/2, ky equals 1/2. Okay, so that sort of makes sense because this does have a stripy pattern to it, right? Diagonal pattern to it, right? So that should be as good of a match as just counting up all the spins. Okay, let's look at this one. Where are we in kx here now? Now we can figure out the sign, right? Sorry?
1/4.
1/4, yeah. Okay, so it's positive 1/4, right? And then where are we in ky? Yeah. And what's the sum? Yeah, 1. Good. Okay. Right, so we're lucky because the plus and minus j's cancel out. Okay. If these didn't cancel out, then you would have a j or minus j in your term. Okay, so your answer can be complex. Okay. And in fact, you know, we'll get to it later, but actually in MR, we actually deal with real and imaginary numbers all the time. Okay, or for those of you who are double E's, it's basically do quadrature detection. So we look at the cosine and the sine components and call those the real and imaginary parts. All right. Okay, so now what we're going to build up to is we're going to start building up to actually what an MRI sequence does. Okay, and a big part of what an MRI sequence does is we actually change the gradients in time. So because the gradients, basically, we need to basically scan through K-space. And the way we do that is by changing the gradients over time, right? And it turns out there's like an infinite number of ways you can do it. Okay, but we're just going to pick, for today, we're going to pick the simplest way, which is called spin warp, which is used right now. There's probably thousands of scans being done right at this moment with that spin warp sequence. For your upcoming homework, you'll look at some other trajectories, like I think a square spiral trajectory. For today, we're going to just focus on spin warp. So just to remind you, we are talking about gradient fields, and this is the notation we'll use. We'll use gx, gy, and gz. And so the field at any location x, y, z, the z component of the field is equal to b0 plus these additional gradient terms, which give you sort of variations that look like this. Right. Okay, but because it's sort of, we want to sort of make our notation a little more compact, we're going to define a gradient vector and a position vector such that gx, x, gy, y, gz is just equal to g dot r. Okay, so sometimes we'll just use this notation. So we can just write bz at any location r is b naught plus g. And notice here, I'm putting in the time dependence here. Okay, because now we're allowing this field to vary with time. Okay. Okay, so let's review precession. So remember, precession is just essentially, if all I have is the main field, it's just going to precess at a theta of t equals minus omega naught of t. Okay, so that theta is just going to be literally increasing with time. Now what I want to do is I want to add, so we have our omega is a function of space and time. So I have my gamma times this bz. So I have the gamma b naught, which is what we talked about, this omega naught precession. But now I have this incremental precession, delta omega. That delta omega is what we use to vary this spatial pattern across our spins. Okay, so let's walk through that. So at every location, we can say that the location at some point, some location r at some time t, it equals the initial magnetization. So 0 here is time equals 0, and I'm multiplying it by some phase. Okay, and that's all essentially, this is all the MR is doing, the gradients are doing, but we want to be able to describe that mathematically. So remember that phase is the angle of the magnetization phasor, and frequency is the rate of change of that angle. Okay, so we can write d phi dt equals minus omega t. Okay, because we're assuming clockwise precession if omega is positive, all right? So therefore, we can just say, well, phase is therefore the time integral of the frequency. So I can always write the phase at any point in time is just equal to minus omega naught t. So that's the overall precession plus this incremental phase d phi. And what's that incremental phase? Well, it's d phi is just equal to the integral of delta omega. And delta omega is just equal to gamma times g dot r. Okay, and so this turns out to be the key equation. So this is just literally, if you look at this, this is just saying there's going to be where I am, what my phase is going to be somehow dependent on the time integral of my gradient. Okay, it's going to turn, that's the picture we're going to want to build up to, that to know where I'm in K-space, I'd simply have to look at the time integral of my gradient. Okay, the time integral. So typically since in the rotating frame, right, we can sort of ignore this term minus omega naught t. So we can just focus on this delta phi term. Okay, because we assume at isocenter that phase is just 0. Okay. Okay, so let's look at the phase with a constant gradient and see if this works. So here is basically this is a function of time. Okay. So, and this is a function of space. Okay. So let's say that I'm here and this is a spin at the isocenter. So over time, it doesn't vary at all. Okay. Now I apply this gradient such that this spin here is going to be faster. Okay. So over time, see, it's accumulated 45 degrees, 90 degrees, 135 degrees. So the delta phase here is just zero, the integral from 0 to this time, t1. So we're this t equals t1 of the delta omega. And that's just going to be given by minus gamma gx x times t1. Okay. And then here, I just go to later time t2, and that just integrates from minus gamma gx x times t2. And then here is just minus gamma gx x t3. Okay. So you can sort of see the more I integrate area under this curve, the more that phase increases. Okay, at any given location in X. So here's the cool thing. Let's say I have a gradient on, I turn it off, and I turn it back on again. Okay. So between this time and this time, it accumulates phase, right? Just like we saw before. But now I turn it off. So during this time, there's no more phase accumulated. Okay, because at this point in time, the relative frequencies of these two spins are the same. So they're not going to change their phase relationship. So this is pretty cool. It means this spin remembers what you did to it. Okay, it's sort of like a memory, right? You basically put a phase on and then you say, well, okay, just remember that. And when I come back to it later, it starts off where you left it off and then accumulates additional phase. Okay, so we've got accumulated 45 degrees here, but there's nothing accumulated here. And then we add another 45. And so here it's at 90 degrees of phase or minus 90 degrees of phase. All right. So that's the main to understand the time varying gradients, just realize we turn gradients on and off. And when they're off, they're not accumulating any more phase. All right. Okay. So we're going to use that sort of understanding to work up to the MRI signal equation. So I know this a lot, so let's work up to it. So this is simply the magnetization at time equals 0. This is the phase term we talked about. And for now, we're also, because of these, I think, I forget why I included this, but ideally, yeah, we want to include the T2 relaxation as well. So this is just saying that magnetization is decaying with time. But in terms of signal equation, we can just carry this around, but we don't need to worry about it too much. This phase is going to have this omega naught term, which is the overall precession. Okay. And then it's going to have this additional term here, which is the delta omega term. And so we can write that as a function of the gradient dotted with the position vector and the time integral of that. Okay. And so what this does is it can take me from a phasor pattern like this, and then at some point later, I have some other phasor pattern here at a place where I have ky along the ky axis. Okay, and then remember, we have to integrate over a volume, right? So I can imagine taking now in 3D, my whole object and multiplying it by this whole thing and integrating over dx, dy, dz. And everything is sort of included in this dot r because this is a 3D vector. But now we're going to do something simple to keep things simple. Let's say I have an object like this, right? So I've got x, y, and z. Okay. It turns out that we'll see later in the class, in MR, I can actually just excite spins in some slice of with delta z. Okay, so I don't have to, in CT, that is determined by the detector. Okay, in MR, it's actually, we'll see it's determined by the interaction of the RF and gradient coils, allows you to just excite magnetization along any slice. Okay, and so this is called slice flexion, which we'll talk about later. For now, just know that we have an ability to just excite magnetization in a slice. Okay, so therefore we can say, well, let's just say the magnetization in that slice is the integral of magnetization in some thickness delta Z, okay? So therefore, we can just worry about what's happening to that two-dimensional image, okay? And so now we have the integral of x over x and y of this two-dimensional object multiplied by this overall phasor term, and then this sort of gradient-dependent phasor term. And then I integrate the whole thing, right? Okay, so the next thing I do is I demodulate the signal. So what happens in MR signal, let's say we have my MRI system, and I get the signal coming off, right? And it's got this e to the j omega naught t term, which just means it's like oscillating at a really high frequency, right? So the first thing I'm going to do is I can actually demodulate it. Okay, I can multiply by cosine omega naught t and sine omega naught t, right? I can, which is basically this, right? This is just cosine omega naught t plus sine plus j sine omega naught t. Okay, so the way I do that in electronics is I just have two paths, right? One path I multiply by cosine, the other path I multiply by sine. So I can I can always multiply by this, which gets rid of, I get rid of this term here, right? It's e to the minus j omega naught t, so I just multiply by the other one, either the plus of it, and I demodulate my signal. So that's what's called demodulation, or bringing it down to baseband, okay? Around DC or around zero frequency. So then my life is much simpler. Now I just have this MXY, and I just have this thing that depends on the gradients. And since I'm only dealing with X and Y, I can write out this dot product as GXX plus GYY. And if I say, well, this has the form, I rewrite this so it's got the form e to the minus j2 pi kxx plus kyy dx dy. And therefore, I can say that, well, kx is just given by this, and ky is given by that. Okay, so the picture is the gradients, the time integral of the gradients tells you where you are in k space. Okay, so essentially, if someone just shows you some gradients, and we'll go through an example later of this together, and you time integrate it, you actually know where you're in k space. Okay, so there's a very simple equation, actually. People have been working on lots of variations of this over time, because basically you have a lot of freedom. So basically, gx of tau, gy of tau, you can design these, right? And so you can design any trajectory you want according to the system limitations. And that will get you through kx and ky in different ways. All right. Okay, so the bottom line is the MRI signal is the Fourier transform of our object. And so the signal is equal to the magnetization multiplied by this complex exponential. And it's a function of time, because I'm going through kx and ky as a function of time. And so therefore, I can say the MRI signal is simply the Fourier transform at kx of t, ky of t. Okay, or else I can write it this way: the Fourier transform of mxy evaluated at kx of t, ky of t. Okay, so this is pretty remarkable that basically just using gradients and RF coils, you can actually make it so that the signal that's coming off the MRI system is essentially the Fourier transform of your object. Okay, so this is just a recap. Remember, frequency is the rate of change of phase. Higher fields give higher frequencies, so the phase will change more rapidly with time. And then we basically use the gradients to make the phase patterns. And if it's a constant gradient, then the distribution of phases changes with time, so it's phase modulation. And the more rapidly the phase changes, then that's a higher spatial frequency, okay? And so at each point in time, the MRI signal is simply the Fourier transform evaluated at these spatial frequencies, okay? And so then the design question becomes, how do we go through k space as quickly as possible or as efficiently as possible? What's the best way to go through k space? Okay, it turns out that there's many answers depending on what you decide to do. Today, we're going to do the most simple one, okay? So let's move on to k space trajectories, okay? So this is sort of the bread and butter of MRI. And I think Yeah, so basically, let's look at what happens if you have a gradient like this. So I just turn it on and turn it off. Okay. So we know that basically from what we've talked about before, the equation is just kx of t equals gamma over 2 pi times the time integral of that gradient. And so this just, as I accumulate area, this just moves me along this line. Okay, I'm just going out to farther and farther points in K-space. And so here I start off at kx equals 0. Here you can sort of see the period is 8, and here the period's 4. So this is going to higher spatial frequencies. So if I just turn on a gradient, I move out to higher spatial frequencies. All right. So let's talk a little bit about those spatial frequencies. So typically, we'll have units of 1 over centimeters. So the spatial frequencies are units of 1 over distance. Gradient strengths are in magnetic field per distance, so Gauss per centimeter or millitesla per meter. So, and gamma over 2 pi has units of Hertz per Gauss or Hertz per Tesla. So if you look at Kx, this equation for Kx, I have Hertz per Gauss, Gauss per centimeter, and then seconds here. So that gives me 1 over centimeters. Okay, so that's our unit sanity check on units. And so let's actually get into how we calculate this. So basically, if this time t2 is equal to 0.235 milliseconds, I integrate this. I use 4257 Hertz per Gauss. This is 1 Gauss per centimeter, and this is the time. Then after this amount of time, I'm saying I'm at a kx of 1 inverse centimeter. Okay, that means if I looked at my object, the spins would repeat their phase every centimeter. Okay, if I applied that gradient. Okay, so remember we said we could talk about turning on and off gradients. So let's look at this gradient, what this gradient would do. So this gradient would turn on, so it's in the x direction. So it's going to move you along this point in K-space, right? There's no gradient in y, so we're not accumulating any area along ky, so we stay at ky equals 0. But now, at this time, we turn off the gx gradient, and we turn on gy gradient. So now we don't accumulate any more phase in the x direction, so we start just moving along the ky axis. So that's how we get to this point in K-space. Okay, so this took us this time and this time. Okay. But let's say you didn't want to wait that long. How could you get out to this point faster? Yeah, you just go this way, right? So just play the gradients at the same time, right? So so in general, you wouldn't ever do this. You would just play the gradients at the same time. Okay. And the other thing is that what you're going to find is that there are limitations on how big the gradient can be. So you don't have infinite gradient strength. And so I think in the upcoming homework, there'll be a MATLAB grader problem where they're asked to design an optimal gradient according to, where you want to be in K-space. And then basically, for example, let's say you want to get out to some place in K-space really fast, right? And you want to get out to you want to do it in time t0, right? And to do that, you need some amplitude A, right? Okay. But the system says, I can't give you that amplitude A, right? So then you're gonna have to redesign it and say, well, okay, if all you can give me, let's say all I can give you, so let's say A is greater than G max, right? So then the system says, no, I can't do that, right? So then in the software, and you'll see this all the time in MRI software code, you're always checking on the gradient limits and different limits. And so it says, okay, well, I can't do that. So you can do Gmax. So then I'll play out something at Gmax, but to keep the same area, now I'm going to have to just play out a bigger gradient, a longer gradient. So now this T1 is going to have to be greater than T naught, such that A times T naught equals Gmax times T1. Okay. So it's a pretty simple, the design problem we're going to give you is pretty simple. Real life gradients don't look like this. They actually look more like trapezoids. Okay. Or there's different shapes, but this is a very common shape. But the design project example we're going to give you, we can just assume rectangular gradients. Okay. And so in that one, you're asked to calculate what you would, sort of to give you a clue as how you go about that problem, you calculate what is the amplitude and time that you think you want to do. And then if you're over the maximum, then you have to go recalculate it and just say, okay, well, I can't use that gradient. So I need to go back and reduce my gradient and increase my time. Okay. So that's pretty straightforward problem, but that'll be coming up later. Okay, so let's take a look at how we go through case space, and we're going to work up to what's called, today. So we'll get through the spin warp trajectory today. So this is now, I'm going to start to show you what an RF pulse sequence looks like, okay, or MRI pulse sequence looks like. So typically it's, we're going to show you what the RF waveform looks like, and you see there's a sinc function. Now, we haven't talked about why this should be a sinc function. We'll talk about that later. But typically, you'll see a sinc function or some other interesting shape, and then you're going to see the gradients. Now, here we're just showing GX and GY, but typically it'll also be a GZ gradient, okay? And here we're just showing you the amplitude. Typically, you might want to see the amplitude and the phase of the RF. But that basically determines everything. Basically, the RF and the gradients, you control those. At every point in time, you can control them, and that becomes the playground for MRI physicists and engineers. Okay, so this RF pulse, for now, just assume it's tipping the magnetization into the transverse plane. So let's just assume this is a 90-degree pulse. Okay, and then I play out this GY gradient, which is going to move me this way, and then I turn it off and I play out the GX gradient, so it moves me that way. So we're just going to go through and look at where we are at different points in time. So at point 1, right, we're at kx equals 0, ky equals 0, right? So there's no spatial variation of the spins, right? At time 2, you can sort of see there's starting to be variation this way. There's no variation this way. I think if you zoom in on it, you can probably see better, right? Okay. So at that time, the period is like this, and I'm at some point in case space along the ky axis. Okay. Then I keep going and playing out that GY gradient. Now at this point, you sort of see the spatial period has halved. So I'm at a farther point out in case space. Okay. And then I turn off that GY gradient and I turn on the GX gradient. So now I go from this point to this point. And so you can sort of see I have this variation in Y. I keep that variation in Y, and now I start adding variation in X, and that gives me a diagonal variation. Right, so things now vary in X and Y, and so I get that spatial pattern, and I'm not at this point in case space, right? And this just shows you a movie of that as you're sort of moving along. So this is what the spins would be doing if you applied those gradients. Okay, so you start to see there was variation in X in the Y direction first, and then you started having variation in X. Yes, question.
On the slide before that, you said that you could say like the RF pulse was 90 degrees.
Yeah.
If that was different, how would that change what we're seeing in case space and on these graphs?
Yeah, let's say we did say, for example, 30 degrees, right? It would still look pretty much the same. Yeah, we'll talk about different flip angles later, like why you would pick different flip angles, but for now, we'll just assume 90 degrees. Okay, yeah. So once we said, as we said before, the most efficient thing is a case space trajectory where we play out the gradient simultaneously if we can. There's no point in waiting, right? So let's do this problem together. Okay, so you'd like to move from the center of case space to kx equals 1 centimeter, 1 inverse centimeter, to ky equals 2 inverse centimeter, right? So I want to move out to this point in case space, okay? And delta t equals 1 millisecond, or 1 times 10 to the minus 3 seconds. Let's assume that gamma over 2 pi equals 4,000 hertz per Gauss. So your thing, and I'll give you a few minutes to think about this, is, and I'll put a poll on Zoom and we'll just do a poll in here manually, is which of these choices will get you to that point in case space based on what we just talked about. Okay, so go ahead and look at that. Think about that, and we'll regroup in a couple minutes. Okay, let's sort of see how people in class were thinking. I see the online stuff, there's been good response. So at the count of three, just sort of yell out what you think the answer is if you're here in person. Okay, 1, 2, 3. B. Okay, yeah, that's the consensus online. Let's check because I haven't done this problem for a while. So yeah, so B certainly could be the answer because this is double this, right? Which makes sense because we're moving out twice as far in K space. So let's just check that. So we want 1 centimeter inverse to equal 4,000 times 1 times 10 to the minus 3 times the gradient, right? So that's equal to 4 times gx, right? And gx equals 0.25 gas per centimeter. Okay. And then obviously gy is double that. Okay, good. All right, here's a slightly more complicated one. I was going to put this on the homework, but or a version of this, but we're going to just do most of it in class. So this is now a more complicated gradient here, where I've got the gx on, and then it actually goes negative. Okay, and then I have the gy on, and it's now a triangle, and it's going up positive and then going negative. Okay, so even though it's negative, it doesn't matter. I mean, you can still integrate it, right? It's just any old waveform. Okay, so let's do 2 multiple choice questions. So the first question is, at 4 milliseconds, what are kx and ky equal at 4 milliseconds? Okay. Okay, let's do an in-class polls. So at the count of three, just say what you think the right answer is. 1, 2, 3. E. Okay, so I heard some B, E, but let's say it's E. Okay, so E is the correct answer, right? Because both of these have zero area once you've integrated over from 0 to 4. Okay, so just know that you can go out in K space and you can come back to the center of K space by just having a gradient with zero area. All right. Okay, let's move on to the next one, which is, well, I don't want to share results. Let's see, relaunch the poll. So now we want to figure out where are you at 2 milliseconds. So go ahead and look at that and see which one you think would correspond to 2 milliseconds. And I think it says assume 4258 Hertz per Gauss, but these answers are different enough that it shouldn't really matter how accurate you are. Okay, let's check in class and see where people are. So at the count of three, just yell out your answer. 1, 2, 3. D. Okay, so it seems like D was the unanimous choice. Not a very popular choice online though. B was the most popular choice online. So let's just work that through. So KX is obviously the simpler one to think about, right? Because we just have to integrate this area. So we take 4258, right? Times 10 times 2 times 10 to the minus 3, right? So that's approximately equal to 4 times 2 times 10. Is that right? Equals about 80, right? So yeah, D would be the closest, right? Okay, without having to do all the intricate math, because that's the only one that's closest. Okay, so that's good. So let's actually draw out where we are in KX and KY, because that'll be important for some of your homework problems. So let's say that's a 2 and 4. So we know in terms of KX, we know that we start at 0 and we end at 0. Okay, and here we go to 85, right? So what does it look like in between? What is the line? Is it in between? What does the curve look like? As I'm integrating a constant area, I just get a line, right? So it just looks like this. Okay, so that's pretty easy. Okay. Let's look at KY. So 2 and 4. Once again, we start at 0 and we end at 0. And in the middle, we get to 42, right? Okay, so we know we're there. What does it look like now? So we're at 1 and 3. Okay, we're integrating a line, so that's quadratic, right? And now we're doing this, so that's going to turn the slope this way, right? And so you're going to get something like this, right? Okay, so the cool thing is all the math you learned in high school turns out to be super useful for MRI. Okay, you just have to remember it. Okay, which I think is, you'll find out in grad school. I think my experience is actually stuff you learn in high school turns out to be more useful than stuff you learn in college sometimes. Okay, all right. Okay, so let's, in the last 5 minutes, I'm just going to scope out what a spin warp pulse sequence looks like, and then we'll talk a little about course logistics. So, because I do want to leave you with this sort of knowledge of, spin warp is essentially probably the most popular pulse sequence out there. If you go and get an MR exam, most likely at least 80 or 90% of your scans, at least for now, are going to be spin warp. Now, I think that's going to change a lot over the next 5 or 10 years as deep learning and AI let us do different trajectories. But for now, the bread and butter of Fourier-based reconstruction is spin warp, okay, or some variation of it. So this is what a spin warp sequence looks like. The GX gradient goes negative and then positive, and the GY gradient looks like this, and it can take on different amplitudes, okay? So we're going to give you some nomenclature. This is typically called the readout gradient. And this is called the phase encode gradient. And this is sometimes called the frequency gradient as well. Okay, so those are just the names in the MR literature that we, so if you hear someone talk about the readout gradient, by definition, it's always the X gradient. And the phase encode gradient, by definition, it's always the Y gradient. That's just, now, there is a distinction though between physical and logical gradients. So we have a physical X, Y, and Z, which is determined by our scanner, and logical X, Y, Z, which is readout and phase encode. Okay, and this typically is slice select. Okay, so that just means that you can have X, Y, and Z physically, but then logically, let's say I rotate things such that X becomes Y and Y becomes Z. Logical X is still readout. Okay, so that's just how we refer to things. So let's see what this gradient does. So initially they're both negative, right? So that's going to take me out to a negative part in K space because I'm accumulating negative area, right? So this takes me out to here, and now I turn off the Y gradient, so I'm not going to move along the KY axis anymore. And then this part here, I just move along the XKX gradient. So this, and as I do this, I'm going to be reading out my data. Okay, so this is going through a line in Fourier space now. All right. So what does this spin warp sequence look like? Here are the RF pulses. So for now, we'll assume each of these is tipping the magnetization by 90 degrees. So every time I tip it, I have some signal and I measure it. Okay. And then I'm going to wait some amount of time, which we'll call TR. We'll talk about that later. During this time, we wait for the M sub Z to recover. Okay. So it's sort of like you have your magnetization, you use it, and then you wait some time, it regrows, and you use it again. And so that's sort of the time component of MR. All right. And then during each one of those, this gradient is exactly the same. See that? You just repeat that gradient over and over again. It's just going here and here. It's just doing this, right? This gradient, though, the phase encode gradient, you can sort of see is changing, right? Here it's negative, more negative. Here it's less negative. So what does that do? Well, the first one takes me out to this place in KY. The next one doesn't go out as far, so it takes me to here. Okay, so now you see how I'm getting different lines in K space now by just changing the starting point. Okay, and then I can keep going, and this one here has 0 gradient in Y, so I just stay along the KX axis. I go out here and then I come back. All right, so in every case, the initial gradients take me out to my starting point, and then I just cross that line. I just go line by line by line through K space. Okay, and I can sort of keep playing that game with more and more gradients. Okay, so actually that brings us to the end of this class. Just in terms of course logistics, the homework, I guess 4 was posted last Wednesday, but since there was a delay in getting on Gradescope, you have till Monday to submit it. But next week is Thanksgiving, so there will be no homework due next week. So, but I'll be posting a homework set this probably by Friday that will be due 2 Fridays from there. So basically you'll have 2 weeks to do that homework set. So it involves some sort of handwritten things, but then some MATLAB grader problems, which have the nice feature that you can actually get immediate feedback. So you don't have to wait for them to be graded. Make sure when you get that assignment, you do read the instructions carefully, because last year, because I'm not sure anyone was here, but there was a strike. So we sort of had, that's when we sort of experimented with the MATLAB grader problems because we didn't have any TAs. So there are suggestions on what you should avoid when you're doing those graders problems, or how you should go about them. But at least this year, you know, the TAs are also here to help you. So that should be good. Okay, are there any questions before we end for today? Okay, if not, I'll be around here to answer questions, and otherwise we'll see you next week.